The pages are 252 through 263. Over the next couple days, that's kind of what we're going to be looking at. Right? A lot of reading involved there. Okay. One, we'll look at electromagnetic radiation, because what happens, if you guys remember from the past, we did flame tests where we got different colors out. You guys remember that? Yeah. And we did the tubes, the gas tubes, and we put electricity through them, and we got different spectrum lines out, or what we call atomic spectrums. Okay? And the reason, because the electron has a dual particle wave-like property. Electrons are a particle. They have a weight. They have a charge. They also have something similar to waves of light, electromagnetic radiation, where they have similar characteristics to those. So they say that electrons have a dual particle wave-like property. Okay? They're kind of like a wave, but then they're also kind of like just a particle, where you can weigh it and quantify it that way. So there's two equations that you need to know a little bit about, actually three equations. The first equation that we have is C equals wavelength times frequency. All right? Lambda times nu. So this is wavelength, and it's measured in meters. So anytime that you plug this into a formula, you got to have it in meters. If you don't, you're going to get it wrong. It's going to be off by decimals. V is, that's the Greek symbol for nu, but that's frequency. And it has a unit where its unit's in the denominator, though. So it's like 1 over seconds, or seconds to the minus 1. That should be minus 1. Okay? Because it's like waves per second, cycles per second, something per second. It's like, it'd be like meters per second, where that unit's on bottom, but it only has one unit. And it's the units seconds in the denominator.
Is that also hertz?
Yes, and then so that everybody in every, can understand that frequency could be in hertz, Hz. So we don't really use hertz much, because that unit really doesn't cancel out. And it doesn't combine with, if we take the wavelength meters times hertz, what's our units? Meters times hertz. But if we do it this way instead, we go meters times 1 over seconds, then what's our units? Meters per second. So that's why we don't really use hertz. Okay? And we know the speed of light is a constant through empty space. So through empty space, it's like 2.998 times 10 to the 8th meters per second. So it's 2.9979 times 10 to the 8th meters per second. I usually use 3. Maybe it's not good to use that, but I usually say it's 3.0 times 10 to the minus, or not to the minus, to the 8th meters per second. Okay? The other equation deals with energy. So we got an equation that says if we got the wavelength in meters, and we got the frequency in seconds, and when we multiply those out, we always get a constant 3 to the 8th for a particular electromagnetic radiation. Energy is big because the electron has energy within the atom. And a lot of times we will preface electron's position, we know a little bit about its energy based upon its position around the nucleus. So well, we'll translate this into energy as well, and energy is equal to Planck's constant, which is h, times frequency. So again, frequency. Now h is Planck's constant. Max Planck came up with this connection that if you could find the frequency, then you could find the energy of the electron. And he tested this in a variety of different ways, and he kept on coming up with this constant, just like you do speed. And this constant is 6.626 times 10 to the minus 34th, and the units are joules times seconds.
It's the negative 34th, you said?
Yes. And the reason why it's so tiny is because an electron is so tiny. So if we would find a frequency and plug in there, and we multiplied it by Planck's constant, we're usually going to get energies out that are like to the minus 18th, 19th, 20th when we start doing it. So let's just say that we have a frequency. Okay, let's just do a couple of these just real quick so you can kind of see them at work with one another. So let's say when we have this frequency, it's red light, and it has a frequency. This red light has a wavelength, okay? And we're going to say that wavelength is 4.1 times 10 to the minus 7th meters is the wavelength. So that's red light. So when we see red light in visible spectrum, that's the wavelength. We magnify it up, we get the wavelength, and we come up to be, actually it's 410 nanometers, but we have to have it in meters, so those are the same. Alright, so that's the wavelength. It's not very, it's just really, really small distance between those two waves. So what I want you to do is I want you to solve for the frequency. What's the frequency of that red light? So go ahead and solve for that real quick. And then we'll get the answer. Setup you'd have is C equals wavelength times frequency. So then we want to find the frequency. So C over the wavelength gives us the frequency. So it would be 3 to the 8th meters per second divided by the wavelength, which would be 4.1 times 10 to the minus 7th. And that's going to be the wavelength in meters. Meters cancel out. You got seconds to the minus 1 will be your unit. And then you'd end up with 7.3. Once you plug it in, it'd be 7.3. When you do your exponents, it'd be 8 minus a minus 7, which would be times 10 to the 15th. But you end up with 0.73 times 10 to the 15th. So it'd be 7.3 times 10 to the 14th. Okay? Any questions you have with that? So the next thing I'd like you to do is take that number, and I want you to solve for the energy of that. A photon. We're going to get into photons, what they are. A photon is a bundle of energy that is sent out by the atom. So this bundle of energy is called a photon, and if that photon has a frequency like red light, then we can solve for the energy of it. So energy, again, is equal to Planck's constant times the frequency. So go ahead and solve for the energy. That particular photon of energy and how much energy it's associated with. going to be a really tiny number. So energy, if it's just based upon a photon, now sometimes if we have like a mole of photons, which would be 6.02 to the 23rd, we'll get a normal size of joules, which sometimes we'll have to be presented with kilojoules. So this is based upon one electron and the energy associated with this one electron that's giving off this energy. Okay, so this would be 6.626 times 10 to the minus 34th joules times seconds, multiplied by frequency, which is 7.3 times 10 to the 14th, and that would be seconds to the minus 1 is what you'd have. Would be on bottom. So if it's on bottom, the seconds cancel. And we're left with joules. So our unit is just joules. Okay? And when we do that, we're going to get a number that's going to be to the minus 20th. But when we take 6.626 times 7.3, we get 48 times 10 to the negative 20th. Well, then we move it over, and so then it becomes 4.8 times 10 to the negative 19th joules. Is that what you guys got?
Yeah.
Okay. So that's really, you got questions related to that, and then you should be able to plug those in and go through that process, because you'll be given some problems like that here a little later to do. Okay. So, why we're studying electromagnetic radiation is because atoms give off light energy when energy is put into them. Okay, we have this. If you look at what's called the Albert Einstein got Nobel Peace Prize for working with what's called the photoelectric effect. Okay, so like, what's the photoelectric effect? Well, it's basically you have some sort of substance. It's probably going to be a metal. Okay, and then what is done is that there's light that's sent in there with a certain frequency. So, specific frequency of light.
Do we need to write this down?
I know. And then you can always go back and watch. Or, no, you don't. Okay? But if you got questions on that, how this works. So this comes in, but it has to be a high enough frequency for something to take place. So if it's a high enough frequency, what comes off are electrons. Will bounce off. Well, not bounce off, but they'll come out. They'll shoot out of the atom. Well, they manipulated the frequency and manipulated the intensity of the frequency. And they did a variety of different things just to see what was happening with those electrons. Sometimes those electrons would come off really fast. Sometimes they would come off slow. And sometimes they wouldn't even come off at all. Okay? The best example that I have here for this would be a vending machine. Okay, you got all these things. This one costs $1. This was 75 cents. This is $1.50. Okay, this one's 50 cents here. Okay, and so you got all these different types of candy and cookies and Pop-Tarts, and you guys, we don't have vending machines here anymore, do we? But like in hotels, right?
We don't have vending machines anymore?
Well, we don't have the candy vending machines
no,
anymore.
we
We used to have them.
We have drinks.
We have drinks and that, but we used to have them. But anyway, for example, this is a coin slot that you would put your money into. So let's say I put in 25 cents and I push this button, could I get that dollar candy bar out? No. Okay? I couldn't push any of these buttons. Okay? They used to, the old vending machines, you guys ever, the old vending machines, they used to have where you'd actually pull. You'd pull on a rod, it'd pull the rod out, and then the candy would drop. Because you'd pull that rod out far enough, then the candy behind would drop, and then it would be positioned back by springs, pushed back. So then the next time you'd go to pull it, you couldn't pull it unless you put your money. That's the way the old ones were. Okay? But now it's like you push a number, right? A1, A5, B, whatever. So, let's say I put in $1. Okay? Put in $1. What can I get for that dollar? I get everything but one of them. I can get this one, and this one. Okay, so what we're getting at, you have to put in a minimum amount of money in which to get whatever food source you desire. You have to put in at least 50 cents if you want to at least get something out of the machine. Okay? Now, what if you put in $1? Could you get 2 of the 50 cent? Yeah, you can get 2 out. Okay? But you could only get 1 of the $1 out. So this money's kind of like frequency. So like this money that you're putting in, okay, it's kind of like frequency. And then if you get these electrons to come out, well, it's based upon what if you have a high enough frequency, or in this case, analogy would be a high enough money. Okay? So going back to this, when you take a look at this drawing, the frequency has to be high enough that you can get it out. So that's called the minimum frequency required. So if you're looking on page 256, they give you 3 statements. I'm not going to write them out. One, in his studies in which the frequency of light is varied show that no electrons emitted by a given metal below a certain threshold. Okay, that's like the 25 cents in that example. I can get nothing for 25 cents. So if the frequency is low enough, it's not going to give off any electrons. Not going to get any out. Second, number 2, for the light with frequency lower than the threshold frequency, no electrons are emitted regardless of the intensity of the light. Okay, so those are kind of similar. Number 3, for light with frequency greater than the threshold, the number of electrons emitted increases with the intensity of light. Do you guys know what we mean by intensity of light? How bright it is, right? Yeah. Like you got dims on your car, and then you have high beam, and that's really intense because if you come up with somebody else on the road and you forget to do their high beams, they click it back and forth right at you. Mm-hmm. So basically it says that the number of electrons emitted increases. So the more you got more electrons out, the more intense the frequency would be. And then number 4 says for the light frequency greater than the threshold, then the energy you get out of the electrons is greater. So that's just saying if you increase the frequency higher and higher and higher, then the electrons that came off with greater speeds. A lot greater speeds. A lot more kinetic energy. Okay? So just think about it in that reference a little bit. So we're not going to do anything where we're going to calculate some values on page 259. We're not going to go through and do some calculations that are associated with mass there. We're not going to do that. So the last thing I want to talk to you today about is on page 261 and then 263. So, all right. So here's the deal. We have hydrogen gas in here. Okay? And then on this side we have negative, and over here this side we have positive. And so we're going to send energy into this, electrical energy. So we're going to send it in here. And this is hydrogen gas. And when we do that, it's going to send out a certain frequency of light. And then that light is going to go this way, so it's going to give off light. It's kind of going to be a pinkish color. What's going to be? And then we're going to go ahead and put it through a prism, and it's going to spread it out. Okay? And when it spreads it out, there's going to be some different lines produced when it spreads out. You're going to get 4 visible lines when you have hydrogen. Okay? And these are spectrum lines. Alright? So for hydrogen, you're going to get one that is kind of an orangish color. I'm going to use red. But it's going to be like right here is going to be red. Okay? That's going to be produced. Alright? And then you get one that's kind of a bluish color. And I don't have shades of these, this makes it bad. But over here, if you're looking at it, you're going to get kind of a bluish color here. And then you'll have another color here that's similar to blue. And then you have a violet. And I don't have a violet over here. So, my color scheme, wish they gave me more. But you're going to have a violet. So this is going to be violet. This is going to be a blue. And then this one's going to be kind of a greenish color. Kind of an aqua color. And then you've got red down here.
You could probably make your own colors on there if you really tried.
I could. I don't know how.
Is there like there's white, yellow, and then there's
The
like
bottom right
the
one.
bottom right. There's like no.
Okay.
Look at like your yellow, like where the yellow is.
Always gives you the 8 squares.
Ah.
Oh,
So the
learn
colors.
learn something every day.
And I think that define custom color coder thing.
Can I do that one? Oh, that's red.
What the heck? I think you might have to.
Define color.
Yeah, that one should be the.
So you could make it lighter or darker if you wanted to on the right side of that.
I think you can choose whatever you
Okay. Well, I'll mess around with that in the future. And I can play around with that. So every time hydrogen does that, you get those 4. You guys remember looking through the spectrum? Okay. So you get those 4 every time. And so these represent electrons, and this will be the last thing. This is all in your reading. So this then represents Bohr's model. Bohr's model is really simplistic. Okay? It's just a model that has its limits. And if you remember with Bohr's model, Niels Bohr, he's a physicist, and he said that there's an electron here, and if you put energy in, then you can cause that electron to move from what's called the ground state to an excited state. So this would be one excited state it could be. It could also, that same electron, okay, that same electron could move up to a second or third energy excited state. That electron could move to a fourth energy state. It could drop back down to a third. When it drops back down, you get a little bit of energy out. Okay. This one could drop back down to the first one. And the bigger the drops, the more energy, the higher the frequency. So if it drops down to that one, then you get a higher frequency out. Now these are going in all directions, not just one direction. Right? And if this one drops from here back down to the original, that might be a longer wave because it doesn't have as much of a drop. Okay? So these are your spectrum lines. This is a spectrum line. Now it may not show up on the visible spectrum because we have blinders on and we can only see what colors? What colors can we see? Red,
yellow,
orange, yellow, green, blue, violet. Can we see ultraviolet?
No.
No. It's over here. I can't see it. Okay, can I see infrared?
No.
No, it's over here. Can't see it. Okay? So there's these different series. They call it like Lyman series, Boston series. Just because we're showing it here doesn't mean we'll actually see the visible spectrum. But there are instruments that will pick it up. We'll be able to read the different frequencies. Okay? So if you turn over page 263, they're actually calculating, I'm not going to have you do this, we've done this in the past, but they can actually calculate the energy associated with a certain constant associated with just hydrogen. It only works with hydrogen. But anyway, you get all these different frequencies of light coming off, and that's how you get your visible spectrums that you can see. Okay? So the bigger the drop, the more energy. So if it goes up here, drops back down to the original ground state, then it's really tiny. Okay? Which one has the highest frequency up here of wave? So if we had 1, 2, 3, 4, which one's the highest frequency?
1.
Number 1. Shortest wavelength, highest. Which one has the highest energy of those 4? 1. Because when we go back to this equation, higher frequency, higher energy. Higher frequency, higher energy. Okay? So, in a nutshell, that's kind of what we went through in differentiated chemistry. Talked about all those points. Then that's kind of the reading associated with that. And then we get the fun of going to the quantum mechanical model with your S's and P's and D's and F's and their location and their spins and all that good stuff. Okay? Which isn't too bad. It's, you guys, the second time you go through it, it gets easier. So you guys pick it up really quick. All right. So I'm going to give you a start of an assignment. And then we'll add to it when we get into what's called electron configurations. This unit will go pretty quick.
Are we going to turn this in?
You will eventually turn this in. Okay? So it's going to be an add-on assignment, so you can at least get started on it. So I'm going to have you do problems on page 299. Do 46, 48. On those, you're given a frequency or a wavelength that you've got to convert into an energy or a wavelength. So they'd be using those two equations I gave you earlier. Okay. We give you 52. 52 is a tougher level question because it's asking you identify the each type of the radiation, and you got to use your table on I think the first or second section of this chapter, and then you need to place them in order of increasing energy or frequency. Is what you need to do with that. Okay, and then a couple more. Okay, 57, related to energy as well. That'll be good. So to do those four.